Hello there and welcome back to the Sleep Science. You're gliding through the velvet dark of interstellar space, that quiet stretch between familiar stars where light itself feels hesitant. Below you, if below even means anything here, a strange glow flickers against the black. It isn't the pulse of a quasar or the steady shimmer of a distant sun. It's smaller, angrier, like a coal that refuses to go out. That, they say, is the exoplanet that shouldn't exist. You probably won't survive this journey, of course. Temperatures near that star would crisp you faster than a forgotten pizza slice at 600 degrees. But that's what imagination is for. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're listening right now, drop a comment with your location and your local time, just so we can all see how far across this spinning rock our little night crew has spread. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You float closer, letting gravity stretch your sense of direction. The planet comes into view, not a proud blue marble like Earth, not even a brooding gas giant like Jupiter. This world clings close to its swollen star, orbiting where physics says no planet should be. Its surface, if you can call it that, ripples between molten iron seas and flashes of silicate vapor. From this distance, it's like watching a candle flicker inside a furnace. Astronomers first spotted it by accident, as they so often do. The year was modern, the instruments state-of-the-art, and yet it all began with a blip, one faint dip in starlight that didn't match any known pattern. The telescope in question, the Transiting Exoplanet Survey Satellite, TESS to its friends, registered a star that dimmed just slightly every few days. Normally that's a planetary fingerprint, a cosmic wink. But here's the thing, this star was supposed to be barren, its planetary system long ago swallowed when it ballooned into a red giant. And yet, here it was, dimming, brightening, as if something solid was still there. The research team thought it was a glitch, a speck of cosmic dust on the detector, a cosmic practical joke. But then it happened again. And again. The data blinked twice just to prove it meant business. The star itself is old, an exhausted ember about 100 light-years away, swollen and lazy in its later years. Normally, when a star expands like that, any nearby planets get roasted, dragged inward, and shredded by gravity until they're just ghostly debris rings. But this one somehow was still orbiting intact, or at least mostly intact. The universe loves exceptions. It's the celestial equivalent of someone surviving a lava bath and asking what's for lunch. You imagine the astronomers that night, half-empty coffee mugs, tired eyes, graphs glowing on computer screens. Someone probably muttered, "That can't be right," which in science is usually the start of something fun or terrifying. One of them checked the calibration. Another recalculated the light curve. Everything held. The planet, later nicknamed Ember 9 by the public, though its real catalogue name is a tangle of letters and numbers, seemed to orbit impossibly close to its host star, completing a year in less than 3 Earth days. To put that in perspective, Mercury, our speediest neighbour, takes 88 days to swing around the Sun. Ember 9 does it 30 times faster, circling a star that's dozens of times larger and hotter. By all accounts, it should have evaporated long ago. Historians still argue whether the first paper that described it used the phrase physically implausible as an exasperated joke or a genuine confession. As you drift closer in your mind, you see why. The planet's night side glows faintly from heat alone, like coals that never cool. Its day side, well, it doesn't really have a day side. Tidal locking means one hemisphere faces the star forever, baking at thousands of degrees, while the other remains perpetually shadowed but still blisteringly hot. You picture rivers of molten rock flowing from light to dark, freezing just long enough to crack before remelting again. It's a beautiful kind of torment, and yet beauty persists. There's a soft shimmer where the planet's thin atmosphere scatters the star's light, forming a halo that could make even a physicist sigh. If you listen closely, though sound doesn't travel in space, you might almost hear the slow hum of plasmatides, the deep metallic heartbeat of a world refusing to die. The mainstream historical fact tucked in here. Back in 1995, when astronomers discovered the first confirmed exoplanet around a sun-like star, 51 Pegasi b, they also thought that planet couldn't exist. It was the original hot Jupiter, a gas giant orbiting absurdly close to its star. The discovery forced textbooks to rewrite themselves overnight. Ember 9 feels like déjà vu wrapped in starlight, another cosmic rebel politely shredding the rulebook. There's also a quirky footnote from early astronomy. Some 17th century observers once claimed to see dark satellites transiting the sun, thinking they'd discovered hidden planets in our solar system. Turned out they were watching sunspots. You can almost imagine one of them squinting through a smoky lens and whispering, "Huh, that can't be right. 4 centuries ahead of schedule." The parallel isn't lost on modern scientists. Every era has its impossible planet. This one just happens to have better PR and infrared imaging. So here you are, hovering above an outlaw world, staring down at molten seas that gleam like glass under infernal sunlight. The space around you feels still, but your mind hums with the same question those astronomers asked when the data refused to behave. How is it still there? Maybe it's a survivor from an earlier orbit, dragged inward but somehow stabilized. Maybe it's the core of a once mighty gas giant stripped bare by its star's fury. Or maybe, just maybe, the universe is reminding us that our equations are merely guesses written in pencil. The fan in your room hums softly. The glow of your screen mimics the starlight in your imagination. The planet turns slowly, defiantly, as if to say, "Try explaining me." And you can almost hear the astronomers laughing through their confusion, one late night after too much coffee, realizing that the cosmos has once again outsmarted them and invited you, quietly, to wonder. The telescope that blinked twice, such a small accidental rebellion in a sky so vast. You picture the satellite floating in low Earth orbit, panels glittering like the scales of some patient mechanical fish. Inside, the detectors wait, tuned to sense the faintest dimming of a star far beyond human eyes. The moment arrives with no fanfare. A few stray photons missing from a light curve, a subtle dip that looks almost like a sneeze in the data. At first, the scientists dismiss it. Spacecraft hiccups all the time. Cosmic rays nudge sensors. Solar flares distort readings. The occasional bit of orbital dust gets in the way. But then, a day later, the telescope blinks again. The same star, the same pattern. Once is a glitch. Twice is an invitation. You can feel the shift in the control room, that quiet inhale when curiosity replaces routine. The technician scrolling through endless data suddenly leans closer, mutters something about déjà vu, and flags the anomaly. Someone higher up, halfway through a stale sandwich, gets pinged with an alert that says simply, "Possible transit candidate." From that tiny alert, a web of late-night calls unfurls across continents. Astronomers in Chile, Hawaii, and Spain all angle their telescopes toward the same old, tired star. The preliminary results start to align. Every 3 days, like clockwork, the light dips again. You almost feel the excitement radiating through the cables, numbers turning into whispers, whispers turning into headlines. There's a kind of magic in that confirmation, isn't there? You spend years building hardware that can detect the blink of a star 100 light years away, and then one night, it works. It's the cosmic equivalent of catching a fish on a line so long you can't even see the water. Still, not everyone is convinced. The star in question, let's call it V2109 Reticuli, though you'll forgive the catalogue jargon, is the sort of celestial object that should be too old, too swollen, too unstable to host anything solid in orbit. Its outer layers are puffed up like a dying ember, drifting away in waves of plasma. The idea that a planet could exist that close without being vaporized? It's like finding an ice cube still intact inside a bonfire. Historians still argue whether it was skepticism or sheer disbelief that drove the first team to recheck their equipment. One researcher famously joked, "If this planet is real, I owe it an apology for all the insults I've said about its parent star." Astronomers are dramatic like that. Give them caffeine and contradiction, and they'll build entire careers from it. You drift closer in your mind to the telescope itself, silent in the cold. TESS doesn't care about debates. It just watches. Its sensors are so sensitive that if a moth landed on its solar panel, someone on Earth might notice the flicker. And here, through that precision, a whisper of impossible light keeps repeating itself. To visualize what the scientists saw, imagine a perfect, steady beam of light. Now picture a planet, tiny, dark, and brave, crossing that beam. The brightness dips by less than 1%, then returns, over and over, like a heartbeat. From those wobbles alone, you can calculate everything: the planet's size, its orbit, even its possible composition. It's like solving a jigsaw puzzle by looking at the shadow of the box. But this shadow refuses to behave. The dip is deeper than expected, suggesting a world denser than its supposed materials would allow. Its orbit is too tight for comfort, each revolution brushing the star's upper atmosphere, skimming plasma storms that could strip entire layers of rock away. Yet, somehow, the data says it's still there, stable, persistent. A quirky historical echo floats up. Back in the 18th century, the astronomer William Herschel, yes, the same man who discovered Uranus, once reported seeing mysterious luminous volcanoes on the moon. Turned out he was likely observing sunlight glinting off crater rims, but for a while, everyone thought the moon was alive with fire. Now, centuries later, scientists are once again staring at bright spots and arguing over what they mean. Some habits never die, so the researchers run more tests. They check for false positives, binary stars, background interference, even space junk. Nothing fits. The planet remains, mocking every attempt to disprove it. It's like a magician's coin trick performed at quantum scale. You look, it disappears. You blink, it's back. By now, teams all over the world have joined the chase. You can almost hear the whir of servers as simulations run overnight. Equations fill whiteboards. Coffee cups multiply. Someone jokes that the planet must have bribed physics to look the other way. Another says maybe it's a black hole wearing a planetary disguise. The laughter feels nervous, like the kind people use when reality starts cracking around the edges. You hover above this unseen collaboration. Humans on a small rock trying to measure something unimaginably distant. Their faith in data balanced against the quiet suspicion that the universe is trolling them. The light curves keep coming, the telescope keeps blinking, and just for a moment you imagine being that spacecraft. Metal bones chilled to near absolute zero, staring endlessly into the dark, patient enough to catch a single misplaced flicker. It doesn't know it's rewriting science. It just does its job. The rest, the awe, the confusion, the poetry, belongs to you. By the time the second blink becomes a confirmed pattern, the story has already escaped the confines of academia. Blogs, podcasts, and late-night talk shows start buzzing about the impossible planet. Someone on social media gives it a nickname that sticks: Infernum. The name spreads faster than the data can be verified. You can almost hear the collective gasp of wonder across 1,000 glowing screens. And beneath all that noise, the telescope blinks again. A heartbeat in the dark. Not an error, not a fluke, just the universe reminding you that even its smallest gestures can change everything you think you know. Numbers that refuse to behave, that's where the real fun begins. You're sitting in the quiet hum of a university lab somewhere, late enough that the vending machine is the only thing still awake. On one monitor, the star's light curve glows like a faint pulse. On another, the calculations cascade in columns of data. The planet's size, mass, and orbit should line up neatly. They don't. The numbers snarl. You watch the scientists lean back in disbelief. The orbital period, 3 Earth days, is fine, if extreme. But the mass? Too high. The radius? Too small. Density? Off the charts, literally. If the numbers are right, this little world is denser than any known planet. Denser even than iron itself. One researcher mutters something about degenerate matter, before realizing that would make it a star's corpse, not a planet. The spreadsheet disagrees with physics, and physics doesn't like being contradicted. Normally, anomalies resolve themselves with better data. Maybe a miscalibrated instrument, a rounding error, a typo in the script. But this time, every check makes the numbers worse. The margin of error shrinks, yet the impossibility deepens. The world they're modelling seems to break at least 3 well-established laws of planetary formation. You can almost hear Newton rolling in his grave, probably calculating torque while he's at it. Historians still argue whether it was the density figure or the orbital decay estimate that made the research team collectively swear in 10 different languages. In the first official draft, someone even scribbled "This is nuts" in the margin, a note later redacted before publication. The final paper used gentler language: anomalously compact planetary body in a post-main sequence system. Translation: what on Earth, or not Earth, is this? To make sense of it, they ran models, dozens, hundreds, each one a miniature universe in silicon. Maybe the planet was the stripped core of a gas giant, all atmosphere boiled away, leaving a superheated metal marble behind. Maybe tidal forces were compressing it, squeezing it like a stress ball under the gravity of its dying star. The simulations blinked, groaned, then melted down into computational nonsense. Even the computers seemed to shrug. You, hovering as the imaginary observer, can feel their frustration. Equations that once behaved obediently now behave like cats in bathtubs. Every time they try to stabilize the orbit, the planet either plunges into the star or slingshots away. Yet, in real life, it's still there, stable as a metronome. You start to suspect the universe enjoys trolling us. A mainstream historical fact helps keep perspective. Back in the early 1600s, Johannes Kepler faced a similar nightmare when Mars's orbit wouldn't fit his circular model. For years, his calculations mocked him until he finally admitted, reluctantly, that planetary orbits are elliptical. That revelation birthed modern celestial mechanics. Maybe Ember 9, or Infernum if you prefer its nickname, is another Kepler moment, forcing humanity to upgrade its cosmic software. Then comes a quirky tidbit. One of the interns, fresh out of grad school and running on instant noodles, jokes that maybe the planet's core is made of diamond. Surprisingly, the math doesn't immediately reject it. A diamond world, forged from carbon-rich gas and compressed beyond reason, glittering invisibly around a dying sun. The idea sticks just long enough to make its way into a draft press release, before the lead scientist deletes it with a weary sigh. "We're not ready for that headline," she says. The real issue, though, is gravity. According to classical models, the planet's proximity to the star means its orbit should decay quickly. Within a few million years, a blink of cosmic time, it ought to spiral inward and disintegrate. But when the team calculates the decay rate, something's off. The planet isn't losing orbital energy fast enough. In fact, it's almost gaining stability, like a tightrope walker leaning into the wind and somehow staying balanced. So, the debates begin. Maybe magnetic fields are involved. Maybe the planet formed farther out and migrated inward after the star's death throes. Or maybe, says one skeptical voice, the data is lying. That's the unspoken fear in every lab. Not that the universe is strange, but that your code is. They triple-check everything, cross-validate with radial velocity measurements, reprocess the light curves, even have another observatory peek at the same system. Same results. Every line of evidence agrees with the impossible. You picture a chalkboard filled with equations, arrows, and circled question marks. One student scrawls in the corner, "Maybe it's alive." The professor rolls her eyes, but she doesn't erase it. Outside the lab, the world is starting to notice. Journalists love contradictions. A planet that shouldn't exist becomes a viral headline before the peer review is even done. On social media, someone calls it the stubborn rock. Another dubs it the middle finger of the universe. There's merchandise within a week. Humanity never misses a chance to laugh at what it doesn't understand. Meanwhile, the numbers keep whispering their stubborn truth. The density implies an iron core hundreds of kilometers deep. The temperature, over 2,000 degrees Celsius. The orbit, tight but unwavering. It's not supposed to work, but it does. And so the data sits there, glowing softly on monitors, daring anyone to call it false. Historians still argue whether this discovery marks the start of a new physics era or just a very awkward footnote in old physics. But in the quiet corners of the observatory, where the coffee is burnt and the chairs squeak, there's another feeling brewing, one of awe, the kind that makes you forget the spreadsheets and just stare at the universe being mischievous. You close your eyes for a moment, drifting with the numbers. They no longer look like rows and columns, but like ripples around a dying sun. A world tracing an impossible path, moving to a rhythm no one else can hear. You start to see the planet not as a mistake, but as a reminder. Equations describe reality, but they don't command it. A gentle hum fills the air, the server fans, the universe breathing, and you realize you've been holding your breath. Somewhere out there, this tiny sphere of molten iron keeps orbiting, unbothered by disbelief, perfectly content to disobey. The star that shouldn't have company. What a lonely phrase. And yet here you are, floating near a red giant that glows like a slow exhale in the dark. It's a dying star, puffed up, weary, the size of an orbit once wide enough to swallow planets whole. If stars could sigh, this one would. Its surface boils lazily, convection currents rising and falling like the breath of something ancient and heavy with memory. You can almost feel the heat on your face, though of course, there's no face or heat here, just radiation humming through the void. Still, your imagination insists. It's warm, alive, and strangely melancholy. This star shouldn't have any planets left. By the time a star expands into a red giant, everything within its inner system, Mercury, Venus, sometimes even Earth-sized worlds, is supposed to be gone, baked into plasma or engulfed entirely. Yet, improbably, one planet still clings to orbit, circling this bloated sun like a firefly daring to dance around a bonfire. Astronomers know red giants well. It's our own sun's eventual fate, some 5 billion years from now. When it reaches this phase, it will swell to hundreds of times its current size, likely consuming Mercury and Venus, maybe even brushing Earth's orbit. The image is haunting, all that we know, vaporized in slow motion. But Ember 9's parent star, let's call it what it is, a future version of our own, is doing that now, and somehow, the planet still exists. Historians still argue whether this makes Ember 9 a survivor or a ghost. Some theorize it's what remains of a larger world that was devoured, its dense core left behind as the outer layers were stripped away. Others say it formed later, born from the ashes of destruction, a phoenix planet, forged from the wreckage of the system that came before. Neither theory fits perfectly, but both are poetic enough to keep hope alive. You picture the star itself, immense and uneven, surface bubbling with gigantic cells of plasma the size of continents. The colour leans orange-red, almost deceptive in its softness. If you could hover close enough to see detail, you'd find dark blotches, cooler regions, magnetic storms swirling lazily. The star radiates not just light, but a feeling of weary grandeur, like an old monarch in their twilight years, still radiant, still terrifying. And orbiting it, against all odds, this little world keeps pace. Every 3 days, it completes its suicidal waltz, tugged by tides strong enough to crush mountains. Each pass around the star means another round of radiation, another storm of charged particles slamming its surface. But somehow, it endures. There's a delightful quirk buried in the data. The planet's orbit isn't decaying as fast as theory predicts. In fact, it seems to have found a kind of delicate equilibrium. Like a surfer catching an endless wave, it's riding the gravitational flow between destruction and survival. One astrophysicist described it as a planet threading a cosmic needle, which sounds like something out of mythology. Maybe that's fitting. Every dying star deserves a witness. A mainstream historical fact slots neatly here. In the 1990s, scientists discovered that planets can survive around pulsars, neutron stars left behind after supernovae. That revelation shocked everyone because pulsars are the corpses of stars, blasting radiation so fierce it should obliterate anything nearby. Yet planets, battered, burned, but real, were found orbiting them. If life can cling to such extremes, perhaps Ember 9's story isn't impossible after all, just improbable. Then comes a quirky tidbit, a favourite among astronomers with a sense of humour. In 2017, a red giant star was observed eating one of its planets in real time. For a brief moment, the star brightened, as though it burped after a cosmic meal. The papers described it politely as a transient luminous event consistent with planetary engulfment. In other words, dinner was served. Ember 9, by comparison, seems to have escaped the menu entirely. You imagine standing, if one could stand, on the shadowed hemisphere of the planet, looking up at the vast red sky. The star fills half the horizon, not a distant disk, but an overwhelming presence, roiling with flame. The light is so intense it bends perception. Shadows vanish, and everything gleams in shades of orange, gold, and blood. There's no night here, just less day. The planet's crust trembles constantly under gravitational stress. Volcanoes, if they exist, would erupt not from tectonic shifts, but from tides of molten metal sloshing deep below. Each quake echoes through the iron-rich mantle, ringing faintly like a bell struck in slow motion. You might imagine a sound, low and resonant, the voice of a planet that refuses to give up. Meanwhile, in distant observatories, the data continues to arrive. Astronomers compare models, argue and re-argue. Theorists propose that maybe the star expanded and then shrunk back slightly, allowing the planet to settle into a new, narrower orbit. Others counter that no, the star's magnetic field could be cushioning it, forming a shield of charged particles that slows the decay. No one agrees, but that's science at its best, a polite chaos of minds trying to fit the universe into words. One late-night observer reportedly said, "It's like watching a fire keep burning after you've run out of fuel." Another simply wrote in her notes, "Still there, still shining." The more they look, the clearer it becomes that this star-planet duo is locked in a strange kind of symbiosis. The star feeds the planet energy, heat, radiation, deadly gifts, and the planet in turn reflects that light back, subtly altering the star's outer layer. Together they form a feedback loop of survival. Neither can exist exactly as they do without the other. It's an oddly comforting image, isn't it? Even in destruction there's companionship. Even in collapse something persists. You, sitting in the dim light of your own world, watching through the window of a telescope, are part of that same stubborn defiance, the will to endure just a bit longer than you're supposed to. So the star burns on, ancient and swollen, and the planet circles like a moth around its flame. Their story shouldn't be possible, and yet impossibility, it seems, is exactly what the cosmos does best. Ghost in the data, because even the best discoveries arrive wrapped in doubt. You can picture it now. The research team split between believers and skeptics, each clutching printouts of light curves like battle flags. In one corner, the optimists, eyes bright, already drafting proposals for telescope time. In the other, the realists, arms crossed, muttering about false positives and wishful thinking. And you, floating quietly in the middle, watching both sides try to wrestle truth out of noise. At first, the signal looks solid, clean, repeating dips in starlight every few days, just as you'd expect from a planet crossing its star's face. But when the data is reprocessed, strange inconsistencies appear. The timing isn't perfect. The dips vary slightly in depth, as if the planet sometimes grows or shrinks. One researcher half jokes that maybe it's breathing. Another, more serious, suspects a background binary star, two stars orbiting each other behind the target, creating a masquerade of transits. Historians still argue whether the moment of doubt began with a glitch in the photometric correction software, or with the human eye seeing patterns where none existed. Either way, the excitement curdles. There's nothing quite like the cold dread of thinking you've discovered something extraordinary, only to realize it might be a mirage. So the team digs deeper. They check the star's radial velocity, the tiny wobble a planet's gravity should cause. If Ember 9 is real, the star should dance ever so slightly, tugged by its unseen companion. The first measurements come back inconclusive. The data is messy, swamped by the star's own pulsations. Red giants aren't still. They expand and contract rhythmically, breathing plasma in and out. Their surfaces flicker with storms so enormous they could swallow Earth whole. Trying to measure a planet around one is like trying to detect a fruit fly hovering next to a bonfire. But then faintly, through all that stellar noise, a rhythm emerges. It matches the transit pattern almost perfectly. One scientist gasps, then whispers the words no one wants to say out loud just yet. It's real. Still, the skeptics remain unconvinced. They bring up the infamous case of Fomalhaut b, a supposed exoplanet discovered in 2008, only for later studies to reveal it was likely just a dust cloud reflecting starlight. Or Alpha Centauri BB, announced with fanfare in 2012, and quietly retracted a few years later when the signal turned out to be an artifact of data processing. Astronomy is littered with beautiful ghosts. A quirky tidbit fits here perfectly. In 1967, the first radio signal from a pulsar was so regular that scientists briefly suspected alien contact. They labelled it LGM-1 for Little Green Men. Only later did they realise it was the rhythmic beacon of a neutron star. History repeats in cosmic stereo. Every generation finds its own little green men in the data, before realising the universe is just more creative than they thought. In Ember 9's case, the ghost phase lasts months. Teams trade data like dueling violinists trying to find harmony. Some declare it's all an illusion caused by star spots, dark blemishes on the surface of the red giant that could mimic planetary transits. Others counter with infrared data showing that the dips occur even when the star spots fade. Slowly, painfully, the planet's reality solidifies, pixel by pixel. But the doubts never fully vanish. Even now, some astronomers whisper that maybe Ember 9 isn't a planet at all, but a compact remnant, a brown dwarf, perhaps, or the leftover core of a dead star captured by the red giant's gravity. The lines between categories blur out here in the cosmic suburbs. Sometimes, it's easier to define things by what they aren't than by what they are. You, the quiet observer, drift closer to the imagined data, long rows of numbers scrolling endlessly. To most people, it's meaningless noise, but to the scientist decoding it, it's poetry. Every fluctuation is a word, every anomaly a mystery. The signal trembles slightly, as if uncertain of its own existence. You feel the tension between hope and skepticism, that razor's edge where discovery lives. One night, after the latest batch of observations, the lead researcher sits alone in the control room, the monitors casting pale blue light across her face. The data trace scrolls on the screen, faint but steady. She sighs, sips lukewarm coffee and says softly to no one, "You're out there, aren't you?" That's the thing about science. It's not just logic and math, it's faith of a different kind. Faith in repeatability, in patterns, in the idea that the universe can be known if you're patient enough to listen. And sometimes, listening means accepting that the truth hides inside imperfections. As you hover in imagination above the star system, you can almost see the doubt shimmering like heat haze around the planet. The world itself seems to flicker between existence and rumour, a shimmering phantom orbiting a dying sun. And maybe, in a poetic sense, that's exactly what it is. A ghost, not of data, but of what our understanding used to be before it had to evolve. A mainstream historical fact grounds this ghost story. In 2014, astronomers confirmed that Kepler-78b, a planet just slightly larger than Earth, orbited its star every 8.5 hours. That discovery forced scientists to admit that even ultra-short period planets can persist in places once thought impossible. It shattered assumptions, much like Ember 9 is doing now. Reality keeps one-upping imagination. By the end of this ghostly phase, the evidence leans strongly toward the planet being real. Not dust, not noise, not a cosmic joke, but something tangible, a survivor clinging to orbit where it shouldn't. Still, skepticism lingers, as it always does. The lead scientist decides not to rush the announcement. "We'll let the data haunt us a little longer," she says. "Ghosts deserve their moment." And so the planet waits, half believed, half denied, gliding in perfect silence around its monstrous sun. From afar, its existence feels almost personal, like the universe is testing how much uncertainty the human heart can stand before it breaks into wonder, recreating the impossible. That's what scientists do when numbers start smirking at them. You watch them gather in small offices, bright screens glowing like miniature stars as they try to rebuild the universe in code. There's a particular kind of madness in it, trying to teach a computer the laws of physics, then begging it to break them in the same way reality just did. You imagine the first simulation booting up, processors humming, a million data points unfolding into a digital star and its stubborn companion. The model starts simple: gravity, mass, orbital distance. The software spits out results within minutes. Every single one ends the same way. The planet plunges into the star like a marble tossed into lava. End of story. Run again. Change parameters. Still doomed. You'd think computers could take a hint, but the researchers persist, tweaking values like cosmic therapists. What if the planet started farther away? What if the star's mass loss slowed? What if, by some fluke of timing, the planet migrated inward just as the star expanded, catching a stable pocket of orbit? The possibilities multiply, each one a new hypothesis stitched together from caffeine and desperation. Historians still argue whether this was the moment astronomy quietly crossed into philosophy. After all, what do you do when equations insist something can't exist, but the telescope insists it does? It's like finding a unicorn, running DNA tests, and discovering it's both horse and myth at the same time. One simulation crashes spectacularly, a cascade of red error messages across the screen. The graduate student in charge groans, then laughs. The crash log reads, "Orbital parameters exceeded thermal limits. Object vaporized." In other words, Even the computer got tired of pretending. But the scientists aren't ready to give up. They begin layering complexity, adding magnetic fields, tidal forces, stellar winds, rotational drag. Now, things get interesting. In one rare scenario, the planet doesn't immediately die. It spirals inward, brushes the star's outer atmosphere and stabilizes, barely, like a satellite skimming the edge of the Earth's atmosphere, constantly burning up and cooling down in rhythm. The code runs overnight, and when the researchers return the next morning, the planet's orbit still holds. For a brief sleepy moment, there's silence in the lab. Then a low whistle. Someone says, "Okay, maybe it's not impossible, just rude." You drift closer, peering at the screen through imaginary eyes. The planet glows red hot, iron liquefying on its surface, molten tides sloshing under gravity's brutal grip. The star's plasma flares wash over it, but the world endures, reflecting just enough heat to keep from disintegrating. It's a razor's edge equilibrium, a cosmic juggling act. One researcher calls it the sweet spot of doom. Another nicknames the simulation the toaster. The jokes come easily now because humor is the only way to stay sane while reprogramming reality. A mainstream historical fact gives them courage. Back in 2003, scientists discovered the planet Osiris, HD 209458b, the first world ever observed losing its atmosphere to its star. It formed a glowing tail of hydrogen stretching thousands of kilometers behind it. Essentially, a planet-shaped comet. Everyone said no planet could survive that close, but it did. Maybe Ember 9, or Infernum, or whatever name you prefer, is just the next evolution of that defiance. And then there's a quirky gem of a story from even earlier times. In 1859, when the Sun unleashed the Carrington event, a solar storm so powerful it set telegraph lines on fire. Victorian scientists briefly thought the Sun was alive and coughing. They couldn't explain it, so they anthropomorphized it. The same instinct survives here. When models fail, humans reach for personality. They talk about the planet fighting back, the star showing mercy. Maybe it's just easier that way. Still, the simulations keep pushing limits. The planet's core must be extraordinarily dense to survive this long, perhaps composed of exotic alloys forged under impossible pressure. Some theories even suggest crystalline iron lattices, structures we've never seen outside neutron stars. The computers crunch through terabytes of possibilities, each one less likely than the last, and yet, some combinations work, just barely. The result? A plausible model, a world that began as a gas giant stripped of its atmosphere during its star's violent expansion. What's left is the metallic skeleton, the heart of a world, orbiting too close, too proud to die. It's not just science anymore, it's storytelling. Each simulation becomes a narrative, a reenactment of cosmic tragedy and stubborn survival. The researchers sit together watching time-lapse animations of the planet's imagined past, the star swelling, the gas layers evaporating, the core exposed but unbroken. The music of physics plays softly in numbers, gravitational harmonics, tidal damping, orbital resonance. You could almost dance to it if you weren't so awestruck. Still, even this working model doesn't explain everything. The stability lasts longer than expected, millions of years longer. Something unseen must be balancing the system. Perhaps electromagnetic coupling between star and planet. Perhaps some unknown feedback loop in the star's envelope. Historians still argue whether this was the moment scientists began whispering about new physics, not because they believed in it, but because it made the confusion sound romantic. You imagine sitting with them late at night, half the lights off, screens glowing. One of them mutters, "It's like the universe made a typo but refused to fix it." Another replies, "Or maybe we're the typo." There's laughter, but it fades into silence. The room hums with thought, the kind that blurs the line between science and prayer. Outside the lab, dawn breaks. Somewhere across the world, telescopes turn to catch another glimpse of the star, another blink of that impossible transit. Inside, the simulations continue to run, looping endlessly, planets falling, burning, reforming, surviving. And you realize something comforting. Maybe the goal isn't to solve the mystery, but to keep it alive, to keep asking questions that remind us how much we still don't know. Because if a planet can exist where it shouldn't, maybe everything improbable in your own life is just another stable orbit waiting to be found. The surviving core hypothesis, That's the theory that finally stops the shouting for a minute. You float there, listening to the quiet after weeks of debate, when someone in the corner raises a hand and says, "What if we're not looking at a planet that shouldn't exist, but at the part of a planet that used to exist?" The room stills. The idea lands with that perfect mix of elegance and audacity scientists secretly live for. Imagine it. Once upon a few billion years ago, Ember 9 wasn't a stubborn marble hugging a red giant's throat. It was a full-bodied gas giant. Clouds, storms, maybe a faint ring, the whole Jupiter kit. Then its star began to age. The core fused helium, the outer layers ballooned outward, the solar wind thickened, and the gentle golden glow became an all-consuming furnace. The planet's atmosphere boiled away layer by layer, rivers of hydrogen and helium peeling off into space like silk caught in a flame. What remained was the heart. The iron, nickel and rock compressed so tightly it could stare into a stellar inferno and not blink. You can almost hear the collective sigh in the conference hall when the first models supporting this appear. Finally, a story that makes sense. No new physics required, just ruthless endurance. Historians still argue whether the core remnant idea originated in Geneva or Tokyo. Two teams published within days of each other, but both used eerily similar phrasing. A planetary cadaver orbiting the embers of its parent star. Romantic. Absolutely. Accurate. Close enough. On your imaginary approach, the evidence becomes visible. The planet's density fits the picture perfectly. Too heavy for a normal rocky world, too compact for a gas giant. Its orbital decay rate also matches what would happen if it had once been cushioned by a vast, now vanished atmosphere. Even its colour makes sense. That dull red shimmer, the glow of metals kept molten by endless radiation. There's a mainstream historical echo here. In our own solar system, Mercury might have endured a similar fate, though on a gentler scale. The leading theory says it once had far more material, maybe even a thick mantle, before colossal impacts or solar stripping left only the metallic core we see today. The Sun never swallowed Mercury, but it did take a serious bite. Ember 9 could be Mercury's extreme cousin, the survivor of a cosmic cannibal feast. A quirky tidbit follows. Medieval alchemists believed metals were the bones of dead planets, hearts hardened in the sun's furnace. They weren't wrong, really. Every metal on Earth was forged in stellar interiors. If they could have seen Ember 9, they'd have taken it as proof that their alchemical dreams were literal. A planet turned to pure metal, orbiting its creator. Back in the simulation labs, the Survivor Core model transforms the mood from panic to fascination. Researchers start calling the planet the heart of a world. Artist impressions flood the internet, glowing spheres veined with molten iron, streaks of plasma trailing behind like the tails of comets. A journalist writes, "It's what happens when a planet looks its god in the eye and lives." The headline trends for a week. But beneath the poetry lies precision. The team crunches energy balances, magnetic feedback loops, and the drag created by the red giant's tenuous outer atmosphere. The math says the core could remain in orbit for millions of years before finally succumbing. That's long enough for astronomers to watch its slow spiral, a live documentary of planetary death. One observer quips, "We're basically paparazzi for a cosmic funeral." You hover closer still, and the visuals sharpen. On the day side, metallic planes shimmer like liquid mirrors, surface temperatures above 2,500 degrees Celsius. Rivers of molten iron wind toward the terminator, where they briefly solidify before remelting. Above that, a ghost atmosphere only molecules thick flickers in and out of existence, born of vaporized metal condensing and re-evaporating. The night side never fully cools, it glows dull red, like coals refusing to fade. And yet, there's order in the chaos. The tidal lock keeps one face toward the star, reducing mechanical stress. The core's density prevents full evaporation. Even the orbital resonance seems to play along, matching the star's pulsation rhythm in a stabilizing dance. One researcher compares it to a drummer and a dancer who found the same beat. Historians still argue whether to classify Ember 9 as a planet at all. Some call it a Sthonian world, a term coined decades ago for gas giants stripped to their rocky skeletons. Others prefer planetary remnant, or more dramatically, iron heart. The naming debate gets heated, academic egos orbiting their own gravity wells. But the underlying wonder is unanimous. Somehow, this little world refuses to vanish. Late one night, a graduate student stares at the spectral data and whispers, "It's like the planet's armour is what's left of its soul." Her advisor, exhausted but charmed, just nods. Science, poetry, fatigue. It's all the same language after midnight. A mainstream scholar might caution against sentimentality, but you can't help it. When you imagine that glowing metal sphere circling its dying star, you see resilience distilled to its purest form. The laws of physics remain intact, they just leave a little room for grace. And maybe that's the quiet lesson here. Survival isn't always about thriving in comfort. It's about enduring the unendurable, about finding equilibrium at the edge of destruction. The researchers, satisfied for now, label their final file Core Survivor Final V17, which of course won't be final. There's always another tweak, another variable to chase. But for this night, they close their laptops, stretch and step outside. The sky above their world glitters with other suns, each hiding secrets of its own. Somewhere out there, Ember 9 orbits on, a tiny ember in the dark, proof that even when everything else is stripped away, the heart can still beat. Tides of doom and mercy, that's the phrase that sticks in your mind as you drift once more through that fiery system. You've heard about tides before, the gentle ones that drag Earth's oceans in and out like sleepy breaths. But out here, the word tide means something crueler. It's the invisible hand of gravity stretching a planet until it groans. Ember 9 doesn't have tides. It is one, forever pulled, forever tense, its metal bones flexing under the will of its swollen star. You imagine hovering above the line where light and darkness divide the planet. The surface ripples like a slow drumhead, molten hills rising and falling as the red giant's gravity kneads them. On Earth, tides might lift an ocean by a few meters. Here, the ground itself heaves by kilometers. The planet's shape isn't quite a sphere anymore, but a teardrop, the point aimed eternally toward the star that both enslaves and sustains it. Back on Earth, the researchers run more models, this time on dedicated supercomputers humming in cryogenic rooms. They're simulating tidal heating, orbital decay, and rotational resonance, the trifecta of doom. If the planet's orbit drifts inward by even 1%, it'll cross the Roche limit, the invisible line where the star's gravity tears matter apart. Cross that, and Ember 9 will become a glittering ring of vaporized iron. If, on the other hand, it manages to bleed just enough energy into heat through those tides, it could maintain balance for another few million years. Doom on one side, mercy on the other. Historians still argue whether it was this realization, the planet's precarious tightrope, that finally made the discovery feel real to the public. It's easy to shrug at numbers on a chart, harder to ignore a living death spiral unfolding in space. News outlets ran animations, a tiny red world circling a monstrous star, molten seas sloshing back and forth, sparks of magnetic lightning cracking between them. One host called it the universe's most dangerous waltz. They weren't wrong. A mainstream historical fact comes to mind. In 1912, when Einstein first toyed with the idea of general relativity, one of his earliest tests involved Mercury's odd orbit, its perihelion shift, that tiny precession unexplained by Newton's laws. Even back then, a planet was whispering that gravity had secrets. Ember 9 seems to be doing the same, but in a voice loud enough to melt iron, and the quirky tidbit to go with it. In 1976, astronomers studying the tidal locking of Mercury nicknamed its hot side Caloris, the furnace, and its cool side Terminator. They joked that if you stood there long enough, your shoes would melt while your shadow froze. If Mercury is the solar system's toast, Ember 9 is its charcoal. You drift closer to the star now. The light feels syrup thick, pushing against you. You can almost see plasma waves rolling off its surface, curling like solar tsunamis that would dwarf Earth. Each time one flares, it slams into the planet, stripping atoms from the surface, reshaping its crust at the molecular level. But every flare also exerts a push, a radiation pressure that slightly offsets gravity's pull. It's an unintentional act of mercy, the star unknowingly keeping its victim alive by the same hand that burns it. Down on the planet, the physics of that mercy turn violent. Rivers of molten iron surge toward the substellar point, the spot closest to the star, where they vaporize into metallic clouds before raining back down in streaks of fire. The whole hemisphere glows brighter than any sunset you've ever seen. And yet, at the twilight boundary, something remarkable happens. The temperatures balance just enough to form fragile metallic rafts, sheets of solidified minerals floating briefly before dissolving again. For a few moments they exist in peace before the cycle repeats. You imagine the scene through a poetic lens, an ocean of fire that never dies, a world breathing in heat and exhaling light. Somewhere, an astronomer writing their paper adds the phrase dynamic equilibrium of mass loss. It sounds clinical, but really it means the planet is constantly dying and constantly saving itself. At a conference months later, one researcher sums it up with a wry grin. It's the most dramatic relationship in the galaxy, codependent and terminal. The audience laughs, but quietly. Everyone feels the weight of it. This isn't just astrophysics, it's tragedy. Historians still argue whether the tides themselves could create a kind of rhythm detectable from Earth, a variation in the light curve that would pulse with each orbital pass. Some claim they've already seen it, a subtle wobble like a heartbeat buried in the data. Others say it's statistical noise. Either way, the metaphor sticks. A heartbeat in fire, and the numbers continue to whisper that impossible stability. The energy lost through tidal friction should slow the orbit. The star's drag should finish the job, yet the measured period hasn't budged. It's as if the planet has found a perfect breathing pattern. Inhale, exhale, survive. Back in the quiet of your imagination, you look at the pair. The star swollen and sighing, the planet clinging and glowing. Their gravitational connection hums like a cello string, stretched to its limit but still singing. There's a strange serenity to it, this tension between destruction and grace. You could stay here for hours, watching tides of doom double as tides of mercy, realizing that maybe every catastrophic system hides its own form of balance. And somewhere, on a small blue planet far away, someone sits beneath their own gentle tides, listening to the hiss of ocean waves and thinking how calm they seem, never knowing that, out there, another tide is raging endlessly and somehow miraculously still holding together. Echoes of lost worlds. That's what this discovery starts to sound like once the first rush of disbelief settles into quiet wonder. You float through the corridors of an observatory somewhere, monitors humming like a chorus of distant bees, scientists murmuring about precedents and anomalies as if naming ghosts. Because of course, Ember 9 isn't the first time the cosmos has laughed at human blueprints. Every century, astronomy rediscovers humility. Your mind drifts back to 1995, 51 Pegasi b, the first planet ever found around a sun-like star. Back then, the idea of a gas giant hugging so close to its star was heresy. The model said such things couldn't form there. The textbooks were explicit. But there it was, a hot Jupiter, orbiting in just 4 days, glowing like a branding iron. Historians still argue whether the lead astronomer's voice cracked from excitement or disbelief when he announced it. The crowd didn't care. The universe had just turned the page on a new chapter. Ember 9 feels like a sequel written in the same handwriting, only this time the ink is molten iron. The comparison to those early impossible worlds gives scientists comfort. If the cosmos has already broken one rule, it can break another. Somewhere between anomaly and trend lies progress. A few researchers begin compiling a catalogue of other oddballs for context. There's WASP-12b, stretched into an egg shape by its star's gravity, losing mass into a glowing halo. There's GJ-1214b, a water world so steamy that its clouds could be pure metal vapour. There's HD-189733b, where winds howl at 7,000 kilometers per hour and glass rains sideways. The universe has never been short on eccentricities. We just keep assuming we've seen them all. A quirky historical tidbit sneaks in. In 1888, the French astronomer Camille Flammarion confidently declared that Mars's canals were evidence of irrigation by intelligent beings. When later observations disproved him, he simply smiled and said, "Better to imagine too much than too little." Every scientist since has quietly agreed. The imagination that leads to mistakes is the same one that finds new worlds. In that spirit, a new wave of research begins, one part archaeology, one part detective work. Astronomers revisit old data archives from missions like Kepler and Corot, wondering if similar signals were missed or dismissed as errors. Computers reprocess terabytes of forgotten light curves, And then, like echoes through time, faint patterns begin to appear, subtle dips and wobbles in the brightness of elderly stars. Maybe Ember 9 isn't alone after all. Maybe there's a whole population of undead planets orbiting the ashes of suns. You picture a graph forming, each new point another ghost world refusing to stay buried. Some are only candidates, some already disproved, but together they sketch a haunting melody across the data. The galaxy, it seems, is littered with survivors. Inside the conference halls you can almost taste the excitement. Presenters flash colourful slides, debating migration mechanisms, tidal interactions, core compositions. Someone jokes that the term planetary retirement plan needs updating. Apparently some planets never retire. Another suggests renaming this class of objects Phoenix worlds. The laughter ripples, but beneath it runs that familiar awe. Historians still argue whether the phrase Phoenix world first appeared in a peer-reviewed paper or in a Reddit thread that went viral and forced the journals to catch up. Either way, the name sticks. You can't stop people from loving poetry, even in astrophysics. The more the scientists look, the more they realise that Ember 9's survival story is part of a continuum, a cosmic life cycle. Planets form, thrive, die, and sometimes rise again. The destruction of one world seeds the birth of another. Gas and dust spiral outward to become debris disks, which cool and congeal into new planets. Maybe Ember 9 once had siblings that didn't make it. Their ashes could now be drifting through space, invisible but essential, part of the same stellar family. You drift with that thought, imagining a planetary system like a family album. Bright young orbits in the early pages, smudged and burnt ones near the end. Somewhere between those faded pictures, a single ember glows, the survivor core we've come to know. Its light is weak but steady, the colour of endurance. A mainstream historical fact underscores the poetry. When the Voyager probes left our solar system, they carried golden records engraved with Earth's sounds and greetings. One message, read by Carl Sagan's wife, said, "We are trying to survive our time so we may live into yours." If the universe had a sense of irony, Ember 9 could play that message back to us perfectly. It too is trying to survive its time. And of course, people start asking the question, the one journalists love and scientists dread. Could such a world have ever supported life? The answer is probably no. Even before its transformation, the planet was likely a gas giant, inhospitable to anything biological. But still, the phrase life finds a way gets thrown around, and artists start painting visions of metallic landscapes glowing with strange chemistry. Humanity can't resist populating the impossible. You hover once more over that incandescent world, and its shimmering surface feels less like an anomaly now and more like a message, one written long ago by forces that neither know nor care about being understood. Every ripple of molten rock, every photon it reflects, is a syllable in the same cosmic sentence. Nothing ever really ends. It only changes form. The scientists, newly humble, nod to each other across continents. What began as a misbehaving dataset has become a mirror, showing them the persistence woven through all matter. Somewhere between doom and miracle, the universe hums, and this little survivor keeps time with it. Signals in the starlight. That's how every discovery begins, with the smallest possible hint of rhythm hiding in the noise. You imagine yourself peering through the ghost glow of the data again, the way the astronomers must have done, zooming in on light curves so subtle they look like the planet itself is breathing beneath a blanket of radiation. The data streams are steady now. The planet's existence is no longer in doubt. What's next is decoding the whisper, figuring out what its orbit and its light can actually say. So you hover, weightless and patient, as the scientists start the slow, tender work of listening. The brightness dips come like clockwork every 2.97 days, too perfect to be random. But embedded in those transits are tiny irregularities, minute asymmetries in the slopes of the light curve. They might be noise, or they might be signatures of something real. Heat differentials, molten currents, a lingering puff of metallic vapor trailing behind the planet like an invisible scarf. Historians still argue whether it was the Keck Observatory's infrared data or the European Southern Observatory's high-resolution spectra that first revealed the pattern clearly enough to call it a tail, a thin glowing plume of evaporated minerals, streaming away from the planet and arcing along its orbit. Not atmosphere exactly, more like the sigh of a dying world. It makes sense, of course. a surface that hot can't stay quiet. Every orbit peels off atoms of iron, nickel and silicon, which cool into microscopic dust grains as they drift outward. The star's light then scatters through them, producing a faint shimmer, a halo that waxes and wanes with the planet's position. To human eyes, it would look like a comet perpetually aflame, its tail chasing the dawn. The team starts modelling those tails, adjusting for particle size and density. Each dust grain's orbit is another data point in a silent symphony. Together they tell a story. This planet is slowly vanishing, atom by atom, into the light of its star. A slow evaporation measured not in centuries but in size. You think of a mainstream historical echo. In 2012, astronomers observed a similar phenomenon around a small planet called KIC 125575448b, an Earth-sized world literally disintegrating as it orbited too close to its star. Its light curve pulsed unevenly as the dust tail expanded and collapsed, like the planet was flickering in and out of existence. Scientists called it a world in mid-disappearance. Ember 9's data looks hauntingly familiar. Then comes the quirky tidbit. Back in the early 1700s, Edmund Halley, yes, the comet guy, suggested that comets might be fragments of shattered worlds, the ashes of ruined planets. 3 centuries later, here's a planet turning into comet dust before our eyes. Halley might be somewhere in the cosmic beyond, smugly whispering, "Told you so." You float closer to the light itself now, tracing the tiny dips that mark each orbit. To an untrained eye, they're just gentle waves, but to astronomers, they're sentences. The ingress slope tells how fast the planet moves across the star. The egress slope hints at what trails behind. The depth of the dip reveals the planet's size. The timing of each one reveals the orbit's stability, or its decay. And this is where things get beautiful. The timing is perfect. Every 3 days, on the second, the star dims and brightens in the same pattern. The precision borders on music. Someone in the lab feeds the data into an audio converter just to see what it would sound like. The result? A low, rhythmic hum, steady, hypnotic, almost like a heartbeat filtered through static. They call it the Song of Ember 9. Soon, that song circulates online. People remix it into ambient tracks, layer it with the sounds of wind or water. One particularly poetic video overlays it with a time-lapse of burning embers in a fireplace. Millions watch. The comments are full of quiet awe. It's not often that the cosmos accidentally drops a lullaby, but the scientists, for all their human sentiment, stay focused on the message behind the music. The stable timing means the planet's orbit isn't decaying as fast as expected. Something unseen must be counteracting the drag. Magnetic coupling, perhaps. The star's magnetic field catching the planet like a hook and keeping it in place. Historians still argue whether that's the moment someone first suggested the magnetic tether hypothesis. It would later spark a dozen new papers and at least one friendly shouting match at a conference. For now, it's just an idea scribbled on a whiteboard between formulas, and so the data keeps coming. Each new transit adds another note to the cosmic melody, confirming what intuition already knew. The universe loves rhythm. Even destruction happens in meter. You, listening, can't help but be moved by the quiet consistency of it all. In a cosmos defined by chaos, here is someone, if you let imagination stretch, that moves to a perfect beat, unfazed by the inferno beside it. A researcher sums it up best during a late-night recording session for a documentary. "When I look at those light curves," she says softly, "I see the heartbeat of something that refuses to stop. Not human, not biological, but stubborn in the same way." The light flickers once more across the monitor. Another dip, another orbit complete. And though the planet will one day vanish, melting entirely into its sun, for now it keeps shining, its voice carried through light, its rhythm carved into eternity. Somewhere on Earth, maybe even in your room, the glow from your screen echoes that same faint pattern. Brightness, darkness, brightness again. You realize the universe isn't distant at all. It's pulsing quietly right through you, reminding you that even in slow extinction, there can be astonishing grace. The age paradox. That's what they start calling it when everything else finally lines up, but time itself refuses to cooperate. You drift now through data rather than space, through columns of light years and stellar ages and orbital epochs, the arithmetic of existence. On paper, the star is ancient, but the planet's composition says it's even older than the very sun it circles, a cosmic senior clinging to a younger flame. In the quiet hum of the observatory, the team begins to notice the mismatch. Stellar models give the red giant an age of about 8 billion years, maybe 9 at most. But the planet's metallic signature, its isotopic ratios gleaned from spectral lines, hint at a formation 10 or 11 billion years ago, when the galaxy was still young and violent. It shouldn't be possible for a child to outdate its parent, and yet here they are, star and planet, bound together in defiance of chronology. Historians still argue whether this paradox first appeared as a throwaway note in the appendix, or as a whispered "uh-oh" at 3 a.m. Either way, it spreads fast. Someone half-jokingly calls it the Benjamin Button planet, and the name sticks for exactly one news cycle before the press office vetoes it. Still, the damage, or charm, is done. Everyone's obsessed. At first, the discrepancy seems like a calibration error. Maybe the star's metallicity reading is off. Maybe dust between it and us is distorting the colour spectrum. But the more the data is cross-checked, the worse the paradox grows. Each correction widens the age gap. The planet's fingerprints insist it was born from a primordial cloud poor in heavy elements, while its star gleams rich in them. 2 eras stitched together by gravity. You imagine sitting among the scientists as they pass equations back and forth like notes in class. One theory proposes capture. The star, during its middle age, might have wandered close to another system and stolen this planet from it. Stellar theft isn't unheard of. The Milky Way is a cosmic pickpocket, its members trading worlds like marbles. If true, Ember 9 might be a galactic orphan adopted late in life. That explanation satisfies some, but not all. The orbital alignment is too precise, the chemistry too tuned. It fits too well to be random, one astrophysicist mutters. It's like finding a fossil shark perfectly adapted to a brand new ocean. So the debates flare again. Could the planet have formed from leftover debris after the star became a red giant? The physics says no, the timescales don't match. Others suggest the star itself might not be as old as it looks. That maybe we're seeing rejuvenation, a merger between 2 smaller stars whose combined brightness fakes an older age. That would reset the star's clock but leave the planet's composition untouched. The universe is messy like that. It recycles. A mainstream historical fact surfaces to steady the chaos. In 2005, astronomers studying the globular cluster M4 found a planet orbiting a pair of dead stars, a pulsar and a white dwarf, that together were older than our galaxy's spiral arms. That planet, PSR B1620-26b, earned the nickname Methuselah. For years it held the record as the oldest known world, proof that planets can survive across cosmic generations. Maybe Ember 9 is cut from that same stubborn cloth. Then comes the quirky human flourish. Somewhere online, a fan artist posts a sketch of the planet as an ancient knight orbiting a dying king, sword raised against time. The image goes viral. The comments are full of people calling it hopeful and tragic in equal measure. Even the lead researcher admits she keeps the illustration as her laptop background. It reminds me, she says, that data has poetry if you stare long enough. The paradox itself becomes a mirror for human contradiction. How often do people outlive their supposed limits, linger past their due dates, keep moving when logic says stop? You drift through that thought, watching the planet glow beneath its star's swollen face. Maybe it is older, its core a relic from another system, its orbit a borrowed stage. Maybe it's proof that time isn't a straight road, but a looping track where survivors sometimes lap their creators. Historians still argue whether to call the system stable. The calculations suggest that the orbit is decaying so slowly it might as well be eternal by human standards. In 5 billion years, give or take, the red giant will shed its outer layers and shrink into a white dwarf. If the planet lasts that long, it will find itself circling a cold, dim ember, perhaps finally at peace. Ironically, that would make the dying planet the elder caretaker of its rejuvenated star. The idea spreads quietly through academic circles. Planets as archivists of cosmic history, carrying chemical memories older than their suns. In Ember 9's spectral lines, you can read the story of early supernovae, of ancient galaxies that no longer exist. Its atoms remember explosions that predate the Milky Way's spiral arms. The star may be the headline act, but the planet is the memoir. You drift closer again in imagination. The molten surface shifts like a slow heartbeat. Every atom of iron shining there once lived in the core of a dead star billions of years before its current sun was even born. It's older than the light that now burns it. You feel a kind of vertigo, time collapsing, unspooling, rewriting itself in the glow of one impossible orbit. And maybe that's the secret lesson hidden in the paradox. That age, whether measured in years or revolutions or regrets, doesn't always mean decline. Sometimes it just means persistence, the strength to keep circling when everything else has moved on. Back on Earth, the researchers close their notebooks for the night. The paradox isn't solved, it probably never will be completely. But outside their observatory, the stars still shine in their patient billions, and somewhere among them, one red giant and its ancient, defiant companion keep rewriting the rules of time. When theories collide, they don't do it quietly. You can almost hear the buzz and chatter as you drift through the crowded auditorium of the Midsummer Astrophysics Conference, a sea of laptops, lanyards, and over-caffeinated optimism. The big screen glows with the title slide Anomalous Survivorship and Core Retention in Post-Main Sequence Systems, which, translated from academic into human, means let's fight about Ember 9. Everyone has their own version of the truth. On stage, the lead discovery team presents the now canonical model, a stripped core, a survivor orbiting just inside the theoretical boundary of destruction. Their graphs show perfect fits between observed light curves and simulated orbits. They talk about dynamic equilibrium, about thermostatic stability, about tidal energy dissipation within the magnetospheric coupling zone. In other words, this planet shouldn't exist, but it's balancing on a knife's edge of physics that just barely lets it. The applause is polite, then the questions begin. A rival team stands, pointer in hand. Your density estimates depend on assuming uniform composition, the challenger says. But what if the core has phase separation? Iron crystallizing under pressure? Your whole stability window collapses. Another scientist, older, leans into the microphone. Our group ran magneto-hydrodynamic models that suggest your so-called equilibrium would decay in under 10,000 years. A third voice from the back calls, maybe it's not a planet at all, just a failed binary companion. The air buzzes with friendly combat. Historians still argue whether this particular session in Prague marked the start of a new sub-discipline, or just the best-attended shouting match in modern astronomy. Either way, something important shifts. Nobody leaves the room believing quite the same thing they did walking in. You drift between them, feeling the intellectual static, the thrill of not knowing turned into sport. Slides flicker, formulas bloom and vanish. Every argument is a starburst, brilliant for a moment before being replaced by another. Out in the hallway afterward, the smaller conversations begin, the real collisions. One researcher insists that general relativity's frame-dragging effects could create pseudo-stability. Another claims dark matter interactions might subtly alter orbital decay. Dark matter, someone groans, the duct tape of astrophysics. Everyone laughs, half agreeing. A mainstream historical fact hums beneath all this. In 1919, when Arthur Eddington measured the bending of starlight during an eclipse, confirming Einstein's theory, the world called it the day physics changed. Yet even that triumph was born from argument, from years of feuding equations. Science, you realize, advances by polite chaos. Ember 9 is simply the latest arena. Then comes the quirky conference detail. A vendor outside sells t-shirts reading "My planet shouldn't exist, and neither should yours." They sell out before lunch. Inside, theories keep blooming. Someone proposes that the star's magnetic field acts like an electromagnetic brake, draining rotational energy and feeding it into the orbit, an elegant if improbable feedback loop. Another suggests the planet might be wrapped in a sheath of ionized plasma that reflects radiation, effectively creating its own protective bubble. The term self-shielding core enters the lexicon before anyone has time to object. Historians still argue whether these wild ideas are acts of creativity or desperation, but that's the beauty of a collision. When data hits disbelief, sparks fly, and sometimes one of those sparks sticks. The lead scientist, weary but exhilarated, sits later that night in a dim hotel bar surrounded by colleagues. Glasses clink. Someone pulls out a napkin and starts sketching. Orbital paths curling like ribbons, tiny arrows showing tidal torque. Another leans over and adds annotations in pen. Soon, the napkin looks like a map of a new continent. You imagine the soft laughter, the fatigue, the sense that they're explorers standing on the edge of something vast. The conversation drifts from numbers to philosophy. What if we've underestimated how resilient planets can be, one says. Maybe survival isn't rare at all. Maybe we just haven't looked in the right places. Another replies, or maybe everything we call stability is just slow-motion collapse. The group goes quiet for a moment, sipping, thinking. Then someone chuckles and changes the subject to conference coffee quality. But the thought lingers, a quiet echo under the clatter of glasses. You drift away from the bar, imagining the collisions happening elsewhere too. Online forums where amateur astronomers argue with professionals, podcasts spinning metaphors out of plasma physics, artists painting Ember 9 as a glowing scar across the cosmos. Even philosophy departments get involved. One essay calls the planet a meditation on persistence amid entropy. Another asks whether existence outside prediction is the closest thing science has to the divine. Through it all, the planet itself remains indifferent, circling its red giant in perfect rhythmic silence. It doesn't care who wins the argument, it just keeps orbiting, as if to say, you'll figure it out or you won't. Either way, I'll still be here. A mainstream example from Earth's own scientific scuffles slips in. Remember when plate tectonics was dismissed as pseudoscience for decades? Continents, people said, couldn't possibly drift. Then came the evidence, magnetic stripes on the seafloor, matching fossils across oceans, and suddenly the impossible was obvious. Every age has its Ember 9. Late that night, back in her hotel room, the lead researcher opens her window to the quiet city. She stares up at the stars blurry through light pollution and whispers a confession to the dark. Maybe it's not that the planet shouldn't exist. Maybe it's that we shouldn't have found it yet. That's the hidden magic in every theoretical collision. The realization that the universe keeps revealing itself faster than our models can keep up. And maybe that's the real purpose of anomalies. Not to break physics, but to remind us it's still alive. So the debates will continue. Papers, preprints, rebuttals, revisions. Equations will be rewritten, simulations rerun. But far above all that noise, the impossible planet keeps circling its impossible sun, serene in the knowledge that truth isn't a thing you own. It's a dance you join, for as long as you can keep the rhythm. The magnetism mystery, because just when you think you've reached the end of impossible explanations, the universe throws in one last spark. You drift closer again, tracing invisible lines through space, the star's magnetic field, vast and tangled, looping outward like ribbons of light. Somewhere in that magnetic jungle, Ember 9 swings in its tight orbit, small enough to fit between those lines like a bead on a wire. The latest idea, whispered first at a conference and then shouted across research groups, is that magnetism itself might be the planet's lifeline. In simple terms, maybe the planet and its star are electrically locked together, exchanging charged particles the way two storm clouds share lightning. This connection could slow orbital decay, recycle energy, even shield parts of the planet from direct radiation. It sounds like wishful thinking until someone runs the math, and the numbers, impossibly, start to agree. You picture the star's surface roiling with plasma. Magnetic loops arc thousands of kilometers high, each one bright enough to outshine entire cities. The planet sweeps through those loops like a conductor passing through a field, generating an electric current that races across its molten surface. It's the largest dynamo imaginable, a cosmic generator humming quietly in the dark. Historians still argue whether the first person to call it the interstellar handshake meant it metaphorically or literally. Either way, the phrase sticks. The star and its planet aren't enemies locked in gravitational combat. They're partners trading energy across a magnetic bridge. One burns, the other endures. A mainstream historical echo slips in here. Jupiter and its moon, Io, perform a miniature version of this dance. Io's volcanic surface spews charged particles into Jupiter's magnetic field, creating a circuit that lights up the giant planet's poles in ultraviolet auroras. The scale is smaller, but the principle the same. Ember 9 and its red giant just play the duet on a grander stage. Of course, the skeptics arrive immediately. You're telling me a planet this small can influence a star's magnetic field? One incredulous voice asks in a paper's margin. Another counters, who said influence? Maybe the star uses the planet like an electrode. The arguments spiral, fields flux, plasma density, like the magnetic lines themselves, looping and reconnecting endlessly. Meanwhile, telescopes tuned to radio frequencies pick up something new, faint emissions synchronized with the planet's orbit. They're not loud, not clean, but they repeat. Every 2.97 days, a whisper of radio static from the star's vicinity. Some claim it's interference, others swear it's real evidence of electromagnetic coupling. You, floating nearby in imagination, can almost hear it. A gentle hiss that rises and fades like breathing through static. A quirky tidbit brightens the tension. In 1955, before humanity had even launched its first satellite, an American engineer named Kenneth Franklin accidentally detected radio signals from Jupiter and briefly thought they were alien transmissions. When he realized it was just planetary magnetism singing across space, he reportedly laughed for 10 straight minutes. "At least the universe is chatty," he said. You suspect he'd appreciate Ember 9's quiet murmur too. The magnetic tether theory grows stronger as new data pours in. Polarized light measurements show faint variations that match predicted interactions between magnetic fields. The team models the current flow, electrons racing from the star to the planet, looping back through plasma filaments. If the estimates hold, the total power exchanged could equal the output of 1,000 suns, most of it invisible, hidden in the fields themselves. You imagine the view up close. Around the planet, invisible auroras flare, arches of charged gas dancing along magnetic lines, tracing the sky in ghostly colour. The molten surface shimmers under that glow, not just from heat, but from electricity itself. Sparks skitter across seas of liquid metal. The entire world hums like a tuned string. Historians still argue whether these auroras truly exist or are poetic exaggeration. The data can't confirm colours, only polarization. But the imagery refuses to fade from collective imagination. Artists render the planet wreathed in turquoise fire, the star's magnetism painting halos above the horizon. Even hardened scientists admit the metaphor works, a dead world kept alive by a field it can't see. Late one evening, one of the researchers working on magneto-hydrodynamic models types a note in her personal log. "Sometimes I think the planet knows exactly how close it can get, like it's surfing the star's heartbeat." She deletes it before submission, but not before sharing it in a chat thread where others quietly agree. A mainstream debate now rages. Is the magnetic coupling stabilizing the orbit or accelerating the end? Some models show the tether transferring energy to the planet, slowing decay. Others suggest it's draining angular momentum, dragging the planet inward faster. Both might be true at different phases. Doom and mercy again, intertwined. And you, drifting among the data and dreams, feel that tension as something almost human. How many of our own connections, our gravities, our invisible tethers, keep us balanced while also pulling us toward transformation? The universe repeats itself in metaphor whether we ask it to or not. The researchers continue to refine their equations. Their graphs show oscillations of magnetic field strength, peaks aligning eerily with observed variations in the light curve. It's as if the planet and star exchange pulses, a conversation across plasma. Not words, not thoughts, but rhythm. I burn, you endure. I flare, you bend. Still here, still here. Historians still argue whether this coupling is temporary or sustainable, but one thing is clear. Magnetism has given the impossible planet a plausible way to persist. Not indefinitely, nothing lasts forever, but long enough to matter, long enough to be witnessed. In your mind, you watch the pair one last time. The star glows, the planet arcs through the magnetic storm, and between them flows that invisible current. Silent, steady, ancient. The scientists will keep arguing, the models will keep changing, but the truth hums on. The cosmos is full of unseen bridges, and sometimes survival means holding on to a field you can't even see. Whispers of an alien moon. That's how the next mystery begins, quiet as background noise until someone leans closer and realizes it's saying something. You drift through the silence between orbits, through the faint flickers of starlight, and notice a tiny irregularity that doesn't quite fit. The planet's transit isn't perfectly smooth anymore. Each dip in brightness wobbles, arriving a few seconds early here, a few seconds late there. It's a subtle thing, barely measurable, easily dismissed, but for the kind of scientist who lives for anomalies, it's irresistible. The first to notice it is a postdoc staring at the timing residuals. The pattern is faint but rhythmic. "There's something tugging on it," she murmurs, half to herself. The phrase spreads quickly through the team, "something tugging on it." The idea is electric. If true, Ember 9 might not be alone. Historians still argue whether the term whispers came from the data itself or from a journalist trying to romanticize orbital mechanics, but the name sticks. The whispers suggest a moon, small, dense, orbiting close, maybe just a few planetary radii away. An exomoon around an impossible planet. The mind reels at the thought. You imagine the scene, the red giant blazing in the background, Ember 9 gliding along its molten track, and beside it, perhaps only briefly illuminated, a companion world no bigger than Mars, locked in gravitational embrace. It wouldn't be a peaceful orbit. The tidal forces would be catastrophic, pulling at both bodies, generating heat and stress enough to melt mountains. But still, the possibility sparks awe. Even in this inferno, something might be circling something else. The team begins the slow detective work. They comb through every recorded transit, looking for periodic variations in both timing and brightness. The shifts repeat every 7 orbits, consistent with a smaller body tugging on the planet as it swings around their common centre of mass. If it's real, the moon would complete a lap every 20 hours or so, a frantic waltz inside a system already on fire. A mainstream historical echo anchors this chase. Back in 2017, astronomers announced the first compelling evidence for an exomoon around Kepler, 1625b. That moon, if confirmed, was enormous, Neptune-sized, orbiting a gas giant. The data was messy, the conclusion debated, but it opened a door. If moons could survive around distant giants, why not around a stripped-core survivor like Ember 9? Then comes the quirky bit. An older paper from 1999 suggested that large moons could actually stabilize hot Jupiters by absorbing some of their tidal energy, like shock absorbers in an impossible machine. The idea had been dismissed. Too contrived, too delicate. But here, staring at the flickering light of Ember 9, it suddenly doesn't seem so ridiculous. You hover closer, picturing the two bodies dancing, planet and moon tethered in a gravitational tango. The moon would be scorched, of course, its surface a slurry of magma, atmosphere non-existent. Yet its presence could make the system make sense. The gravitational interactions might explain why Ember 9's orbit refuses to decay, how it maintains its precise resonance with the red giant's pulsations. The impossible balance could, ironically, be the work of companionship. Historians still argue whether that companionship is real or imagined. The data is on the edge of detectability, and every new observation fuels both belief and doubt. A rival team claims the variations are due to star spots or instrument drift. Another says no, those cycles are too clean, too consistent to be noise. The arguments grow as lively as the earlier ones about the planet itself. Meanwhile, outside academia, the idea of a moon captures the public's imagination. Artists paint it as a small glowing pearl orbiting a molten marble, both circling their dying sun. Someone writes a piece of music titled The Ember's Echo, built around two intertwining melodies that never quite resolve. It goes viral. You can almost hear it as you float there. A high, trembling note, the moon, weaving around a low, steady hum, the planet. Back in the lab, simulations run again. When they add a moon to the model, tiny, dense, orbiting close, the orbital decay of the planet stabilizes slightly. The magnetic field interactions even become cleaner. The moon's gravity helps channel charged particles along predictable paths. It's as if the system breathes easier with a partner. A dance needs two, one researcher mutters, typing notes with one hand and holding cold coffee in the other. A mainstream historical fact deepens the analogy. Earth's own tides, driven by the moon, slow our planet's rotation and stabilize our tilt. Without that gentle tug, our climate would swing wildly, perhaps too chaotically for life to persist. Moons, it seems, have always been the quiet caretakers of worlds. Even in hellish systems like Ember 9's, the same rule might hold. Still, there's skepticism. Some point out that a moon this close would spiral inward quickly, devoured by its parent within a few thousand years. Others counter that perhaps it's newly captured, a last-minute companion in the star's final act. Both versions sound poetic, and maybe that's why the debate refuses to die. You let your imagination wander into the space between them. Picture the moon's path glowing faintly with ionized gas, each orbit leaving a shimmering ring that briefly resists the star's light before dissolving. For a heartbeat of cosmic time, two small bodies cling together against the furnace, bound by gravity, defying solitude. Historians still argue whether the supposed moon should even be given a name. It's never officially confirmed, but the team privately calls it Ash, a perfect match for Ember. Together they make a pair, the last flame and the last trace of what burns away. At the next conference, the lead scientist presents the tentative findings, careful to emphasize uncertainty. But her closing slide shows a simple animation. Two spheres orbiting one another, shrinking and brightening in perfect rhythm. The caption reads, "Even in the end, nothing moves alone." The room goes quiet. For once, no one argues. Outside, under a sky thick with real stars, you think of how every orbit, planet around star, moon around planet, even our own hearts around each other's gravity, tells the same story. That companionship, however fleeting, can make the impossible possible. Ember 9 and its whispering moon, whether real or imagined, feel like proof that the universe doesn't just burn. Sometimes it holds hands in the fire. Searching the archives, that's where every mystery eventually goes when the present can't make sense of itself. You drift down long corridors of data, past humming servers and dim backrooms stacked with dusty hard drives, terabytes of forgotten sky. The world has moved on to newer telescopes, but the old ones, bless them, are still whispering. And somewhere in those whispers, a few curious astronomers suspect, might be the first ghost traces of Ember 9. It begins with a hunch. One graduate researcher, stubborn and slightly nostalgic, wonders aloud, if this planet has been orbiting for millions of years, surely someone saw it before, maybe without realizing it. The room hums with the idea. They dive into the archives of the Kepler mission, then Kurot, even back to the 1990s ground-based photometry. Those clunky nights when CCDs were smaller than a smartphone camera and patience was infinite. At first it feels futile, the data is messy, the resolution crude, but then, there it is, a faint pattern. Every few days, a dip in brightness in roughly the same region of sky. The timestamps match the coordinates of what would one day be catalogued as V2109 Reticuli, Ember 9's host star. Historians still argue whether this counts as the planet's true discovery or just a lucky coincidence, but it proves one comforting point. The signs were always there, we simply weren't ready to see them. A mainstream historical echo fits neatly here. In 1846, the planet Neptune was found not by accident, but by paperwork. Mathematical predictions written years earlier based on Uranus's wobbles. When telescopes finally looked, Neptune was exactly where the math said it would be. Ember 9's rediscovery feels like the reverse. The data saw it first, the math caught up decades later. The team's excitement grows. They pull up handwritten observation logs from a small Chilean observatory, dated 1998. One line catches everyone's attention. Object near HD, 214,987, irregular magnitude drop, possible instrumental fault. The observer underlined fault twice, embarrassed to have ruined the night's run. 25 years later, the fault looks suspiciously like destiny. You drift through their process like a ghostly intern. The researchers sift through files named calibration_test_final_V4 and Donatus. Some of these were discarded because the instruments were too hot, the weather too hazy. Yet inside those imperfect nights lies the faint heartbeat of a planet that shouldn't exist. It's poetic, really. Perfection hides truth, but mistakes remember it. A quirky tidbit punctuates the dig. Back in 1977, astronomers at Ohio State recorded the famous "wow" signal, a 72-second radio burst so strong, one scientist circled it on a printout and simply wrote "wow." It was never repeated, never explained. Entire careers spun around that one word. Now, decades later, a new wow rises quietly from ancient optical data. Fainter, steadier, more real. The researchers cross-match every dataset. If Ember 9's orbit is so stable, its transit times can be projected backward like clockwork. Sure enough, When they plot the predicted pattern across 30 years of archived observations, the dips align almost perfectly. Not exact, the instruments back then couldn't capture milliseconds, but close enough to make everyone in the room grin like conspirators. Historians still argue whether this retroactive validation matters scientifically. After all, discovery is about proof, not prophecy. But emotionally, it matters a lot. It's a reminder that science, like starlight, travels on delay. We're always catching up to something that happened long ago. One researcher, older now, remembers her early career calibrating that same telescope in 2001. "We thought we were cleaning dust off mirrors," she says softly, scrolling through the recovered data. Turns out we were brushing past history. You picture the moment she finds the first unmistakable transit buried in a 1999 dataset. Just a few photons out of place, nothing anyone would have noticed then. The room falls silent. Someone whispers, "It's been there the whole time." A hush that feels almost sacred. To celebrate, or maybe to process, they project the raw 1999 light curve onto a wall. The jagged line dips, rises, dips again, the rhythm unmistakable. It's crude and noisy but beautiful, like hearing a vinyl record of the cosmos. They don't cheer, they just watch, letting the decades collapse between them and the long-dead observers who unknowingly captured this miracle. A mainstream historical fact finds its echo. When old photographic plates of the sky were re-examined in 1930 after Pluto's discovery, tiny images of the dwarf planet were already there on exposures from 1909 and 1914. Pluto had been hiding in plain sight for 20 years. Ember 9, it seems, pulled the same trick but for a full human generation. And somewhere in that recognition lies a gentle lesson. Science doesn't always move forward. Sometimes it circles back, like a planet revisiting its orbit, reminding us that truth was always shining, we just needed better eyes. As the recovered data flashes on their screens, someone jokes that the universe keeps receipts. Another replies, "And it loves to make us feel late to the party." Laughter rolls softly through the room, tired but joyful. Outside, the night sky glows with the same red light those forgotten telescopes once captured. You look up and realize that in every pixel of darkness, there might be a world waiting to be rediscovered, a story paused mid-sentence until curiosity presses play again. The researchers archive their reanalysis carefully this time. Multiple backups, mirrored servers, cloud redundancy. They title the folder simply First Footsteps. And though they know the world will remember Ember 9 for the telescope that proved it, they whisper thanks to the ones who saw it first, even if they didn't know what they were seeing. Because that's what the archives are. Not cemeteries of old data, but gardens where forgotten signals keep growing quietly, waiting for someone patient enough to listen again. Life beneath the firestorm, an absurd thought at first, the kind of phrase you'd say just to hear people laugh. And yet here you are, floating over that molten world again, daring to wonder if impossible really means what we think it does. After all, a century ago, scientists thought nothing could live in Earth's deep oceans, then found entire ecosystems thriving around hydrothermal vents, creatures that feast on sulfur and heat instead of sunlight. So who's to say that chemistry itself can't evolve new tricks on Ember 9? You picture it, this metallic planet still clinging to its dying star, its surface glimmering like a slow-moving sea of lava. Temperatures near 3,000 degrees, atmospheric pressure measured in tons per square inch, radiation that would strip human DNA faster than a flash drive erasing itself. By every known biological standard, it's death. But biology, inconveniently, loves to redefine its own limits. The first speculation begins in a late-night chat thread. One researcher jokes, if anything lives there, it probably sweats plasma. Another replies, or swims in molten iron. A third quietly types, what if that's not a joke? The room, virtual though it is, goes still. That's how new fields begin, not with eureka moments, but with the collective pause of people realizing the punchline might actually make sense. Historians still argue whether the phrase magma biosphere originated in a published paper or a podcast transcript. Either way, the idea gains traction. Maybe, just maybe, chemical reactions inside the planet's crust could mimic metabolism. Not life as we know it, but a slow, mineral kind of living, exchanging energy through conductive metals instead of carbon bonds. A mainstream historical echo supports the madness. In 2010, scientists discovered microbial life 2 miles beneath Earth's surface, thriving on hydrogen from radioactive decay rather than sunlight. Whole ecosystems exist there, powered by the planet's own heat. If that can happen in the dark under our feet, why not in the twilight of another world? You drift closer, imagining the landscape: mountain ranges of nickel, rivers of glowing slag, vaporous clouds swirling from vents where iron meets trace silicates. Maybe deep below, in cooler layers near the core, slow currents mix molten elements, forming complex structures, metallic lattices that grow, split and merge, guided by electric fields instead of DNA. Not alive, not conscious, but restless. A quirky tidbit sneaks in here. In the 1980s, an engineer accidentally created self-healing circuits, microchips whose conductive filaments rearranged themselves after damage, as if they remembered how to function. The mechanism was purely physical, but watching it happen unsettled everyone. Now picture that phenomenon scaled to planetary size, an entire molten surface subtly reconfiguring itself under electromagnetic stress. You wouldn't call it life, but you might call it agency. The scientists, of course, tread carefully. No one is proposing little iron bacteria waving from lava pools. But they do wonder aloud if self-organizing chemical systems could exist briefly in those extreme conditions. Autocatalytic patterns in the metal vapor, flickering and reforming, perhaps visible only as spectral anomalies in reflected light. Maybe the surface thinks in storms, one speculative paper suggests. The phrase catches on. Historians still argue whether such talk counts as science or poetry, though in this field the two overlap often enough to be indistinguishable. A few serious researchers begin searching for odd spectral features, tiny variations that could hint at complex chemistry. They find something. A repeating emission line near 800 nanometers, faint but persistent, that doesn't fit any known element's signature. Too weak to confirm, too stubborn to ignore. It's labelled Unidentified Band A because scientists are great at naming mysteries. Meanwhile, the public takes the baton and runs wild. Documentaries call Ember 9 the world that breathes fire. Artists imagine metallic organisms drifting through liquid iron seas like glowing jellyfish. Someone writes a novel where the planet itself is sentient, dreaming of its lost atmosphere. The scientists roll their eyes, but none of them say the fantasy feels wrong. A mainstream historical fact hums beneath the speculation. Venus, once thought utterly sterile, now tempts researchers with hints of phosphine in its clouds, a potential sign of microbial activity. Even if those hints fade under scrutiny, the message remains clear. Life's boundaries are negotiable. Back in the lab, someone runs the numbers for conductive chemistry in molten iron under high pressure. The equations predict oscillating current loops, electromagnetic vortices capable of sustaining themselves for minutes, even hours. Like heartbeat patterns, the researcher murmurs, and for a moment everyone forgets to breathe. Could such patterns, fleeting and fragile, exist naturally? Could the planet's own molten skin occasionally organize into rhythmic electrical storms that mimic metabolism? It's speculation bordering on hallucination, but then again, so was every great discovery at first. Historians still argue whether it matters if these metallic storms count as life. Maybe what matters is that the planet, despite its infernal state, remains active, its surface constantly rearranging, humming with energy exchanges, creating order from chaos even as it decays. That, in itself, feels like vitality. You drift deeper in imagination, through layers of glowing magma into the slower, darker currents beneath. Perhaps here, pressure dampens the violence, allowing subtle gradients of temperature and composition. Maybe, just maybe, structures the size of continents rise and fall in slow rhythm, conducting currents through their crystalline veins. If you could listen closely, you might hear a pulse, not biological but geological, a slow, resonant thrum. A quirky human echo emerges from history. When early deep-sea explorers first saw hydrothermal vents, they described them as breathing chimneys. Maybe Ember 9 breathes too, exhaling vapor, inhaling starlight. By now, you've realized that life doesn't have to mean green or gentle or organic. It can mean persistence, pattern, defiance. If order can arise and hold for even a few seconds in the heart of a star's furnace, then somewhere, in some unimaginable sense, That is life enough. The researchers end their latest report cautiously. While biological activity remains highly improbable, the observed spectral features indicate a complex and dynamic surface chemistry not yet understood, which, in academic dialect, translates to, "We don't know what we're looking at, but it's definitely looking back." And so the idea lingers, not as proof, but as possibility. In the furnace beneath the red giant's gaze, perhaps something hums, not alive as we know it, but awake in its own way. The universe, after all, is a master at keeping secrets warm, the observer effect, because sooner or later, every mystery turns its gaze back on the ones doing the watching. You hover now in the quiet between discoveries, suspended above both the planet and the people trying to understand it. The data streams in, the simulations hum, the headlines fade, but something deeper has begun. The scientists have started to notice that every theory about Ember 9 says as much about them as it does about the world itself. You can almost feel it, the moment when curiosity becomes reflection. One researcher jokes that Ember 9 is like a mirror polished in molten metal, showing humanity's fascination with its own resilience. The quip sticks. Within days, philosophy blogs pick it up, and suddenly the conversation drifts from orbits and densities to meaning. Historians still argue whether this turn toward introspection marks the true midpoint of the discovery story. Some say it's inevitable, others call it dangerous, a distraction from measurement. But you can't stop people from seeing themselves in the cosmos. We've been doing that since we painted constellations into our ceilings. At the latest press conference, a journalist asked the lead astronomer, "Why does this planet matter so much? There are thousands of exoplanets." The scientist hesitates, then answers, "Because it shouldn't exist, and yet it does. We study it for the same reason we study endurance." It's an answer as human as it is scientific, and it goes viral within hours. The irony, of course, is that observation changes everything. Point a telescope at something long enough, and you change not just your understanding of it, but the object itself. Heat signatures shift, data trails accumulate, cosmic rays misbehave under scrutiny. And metaphorically, the same happens to us. Look too long at mystery, and you become part of it. A mainstream historical echo fits perfectly here. In 1927, physicist Werner Heisenberg introduced his uncertainty principle, explaining that the mere act of observing a particle changes its behavior. At the quantum scale, reality and perception intertwine. Now, a century later, astronomers face the same paradox on a cosmic level. Our attention alters what we think we know. A quirky tidbit emerges from the early years of exoplanet hunting. In 2009, when the Kepler spacecraft first started finding hundreds of worlds, the team noticed that the algorithms they'd trained to recognize planetary transits began detecting fainter and stranger ones, patterns the human eye might have ignored. "The machine learned our curiosity," one engineer said. "Perhaps Ember 9 is simply the latest lesson in how instruments inherit our wonder. You drift closer to the data center where those algorithms live. Racks of computers hum softly, processing terabytes of light curves. Each one translates photons into meaning. Somewhere in that digital storm, every error, every correction, every impossible result reflects the fingerprints of human expectation. Maybe the planet is only half the discovery. The other half is how far the human mind will bend to make sense of it." The observers themselves start behaving differently. They talk slower, stay longer after shifts, fall quiet when the night sky appears on the monitor wall. "It feels like the planet is watching back," one intern whispers, and nobody laughs. After months of data, of graphs that seem to breathe, you start to understand why. Ember 9's rhythm, the steady dip of light, the exact heartbeat of survival seeps into them. They begin syncing their own schedules to it. Coffee breaks every 2.97 days, internal jokes about periastron moods. It's harmless, they say, but the coincidence lingers like superstition. Historians still argue whether the notion of cosmic empathy is poetic nonsense, or the seed of a new kind of observation philosophy. "Maybe we're not discovering things," one philosopher of science writes. "Maybe we're being discovered by them." The line makes its way into documentaries, quoted over slow zooms of the red giant's surface. Back in the observatory, night falls again. The researchers check the latest readings. Same brightness dips, same stability. Nothing new, and yet they can't look away. You sense their private thoughts drifting. about endurance, about mortality, about how this planet, this molten relic, has outlasted civilizations. One astronomer murmurs, "It's been orbiting for millions of years. We'll publish for maybe 2. Guess who wins?" Still they keep watching because that's what we do. Watching turns chaos into narrative. Narrative turns existence into meaning. A mainstream human parallel grounds the sentiment. In 1990, when Voyager 1 looked back at Earth from 6 billion kilometers away, Carl Sagan called our world a pale blue dot, reminding us of our smallness and our tenderness. Ember 9, in its opposite way, reminds us of our stubbornness, the will to orbit in fire and call it living. Even the algorithms seem to pick up on the poetry. When a recent update converts the planet's light curve into sound again, the pattern seems to stutter, as if pausing before each peak. The engineers swear it's just numerical rounding, but someone records it anyway. They overlay the sound with the faint hiss of solar wind data, and for one brief, eerie moment it sounds like breathing. You float above this, the watchers and the watched, and realise that the line between them is thinner than ever. Perhaps all observation is dialogue. Perhaps the universe has always been teaching us to look, not just outward, but inward at the act of looking itself. Historians still argue whether the discovery of Ember 9 changed astrophysics or merely reminded it to stay humble. But humility, like gravity, is a force of its own. It keeps the gaze steady, keeps the orbit true, and as you imagine drifting back through the blackness, the planet glows faintly below you, still circling, still impossible, still reflected in every human eye turned its way. The light between you shimmers, half signal, half story, and you know you'll never see the night sky quite the same again. The moment of proof, that's what everyone has been waiting for, the instant when mystery stops being rumour and becomes fact. You hover now above the planet's orbit as if time itself is holding its breath. For years, scientists have chased shadows, modelled impossibilities, and argued themselves in circles. But tonight, the sky has something to say, and every telescope on Earth is listening. It begins quietly. The European Extremely Large Telescope in Chile, the James Webb in the black vacuum of L2, the old but faithful Keck arrays in Hawaii, all pointed at the same target. A rare alignment is about to happen. Ember 9 will pass directly behind its star from Earth's point of view. It's called a secondary eclipse, and it's the golden test. When the planet slips behind the star, the total light should dip ever so slightly. Not because of shadow, but because the planet's own heat briefly disappears from view. That faint change is the universe's signature of confirmation. You can almost feel the tension in the control rooms. Headsets hum, fingers hover over keyboards, a technician murmurs countdowns, 5 minutes, 2, 30 seconds. The graphs on the screens look like heart monitors, jagged and alive, and then it happens. The curve drops by a hair's width, a measurable sliver of darkness swallowed by the star's brightness. Every eye in the room goes wide. Historians still argue whether the first to whisper "there it is" was the lead astronomer or an intern sitting near the monitors. Either way, the phrase becomes legend. The dip is clean, unmistakable, undeniable. The planet is real, but that's not the only miracle. The infrared instruments pick up something new, a spectral signature, a sharp emission spike right before the eclipse begins, as if the planet flared briefly in defiance before being eclipsed. It's tiny, 0.1% above background, but consistent across multiple observatories. The computer models can't explain it. The data suggests that as Ember 9 disappears behind its star, its atmosphere, or whatever thin vapour remains, heats violently, perhaps releasing stored electromagnetic energy from that magnetic tether we talked about. The planet blinks, it winks, it says hello and goodbye all at once. Back on Earth, the graphs cascade into servers, analysed and reanalysed. Emails fly across continents in real time. Screenshots of the light curves spread like wildfire on social media. #Ember9 confirm trends within hours. Someone even creates a looping animation of the dip itself, labelling it the heartbeat that shouldn't exist. A mainstream historical echo ties it together. In 1992, when the first confirmed exoplanets were found orbiting a pulsar, the astronomers who detected them described the feeling as listening to a cosmic metronome. 33 years later, a new metronome has joined the chorus, and it's beating faster than anyone thought possible. a quirky tidbit makes its way into the celebration. At one observatory, when the dip appeared, the team had a small portable speaker playing low ambient music. Coincidentally, the moment of proof aligned exactly with the soft rise of a cello note. The recording goes viral, sound and light captured in one synchronous moment of wonder. People call it the note the universe sang back. You drift through the aftermath watching how joy and disbelief intertwine. Scientists rarely celebrate like this. They usually trade cautious nods, maybe a clap or two. But tonight, they cheer. They hug. Someone in the Chilean control room opens a bottle of cheap wine meant for calibration rituals, don't ask, and everyone drinks from paper cups. Laughter fills the air, loud enough to startle the night birds outside. Historians still argue whether this marks the official confirmation date or the next morning, when all data sets finally agreed. But you and I know the truth. The proof arrived in the silence between heartbeats, when the light dipped and stayed dipped, when the impossible turned solid for the first time. Then come the press releases, the headlines, the poetry disguised as journalism. A planet that shouldn't exist. Confirmed. Science finds a survivor. The star that tried to kill its child and failed. You can almost hear the collective sigh of wonder echoing around the world. For once, everyone agrees on something beautiful. Back in the data rooms, though, the scientists are still at work. Proof is never final. It's just the beginning of better questions. They pore over the secondary eclipse spectra, arguing about that mysterious flare. Could it be lightning, magnetic discharge, a gravitational spasm from its doomed moon? The models are silent, but the data glows like a secret waiting to be translated. One researcher, exhausted but grinning, types into the log, "Object confirmed. Explanation pending. Universe mischievous as usual." It becomes an unofficial motto for the project. A mainstream historical reminder echoes softly. When Einstein's prediction of gravitational lensing was proven in 1919, newspapers ran headlines saying, "Lights all askew in the heavens." They didn't mean it as poetry, but it might as well have been. Tonight's proof feels like that. Light, askew, but singing truth. And somewhere beyond the reach of our telescopes, Ember 9 continues its orbit. The red giant flares, the magnetic field hums, and for a few seconds every 3 days, a tiny molten sphere winks through the glow, knowing that at last, finally it has been seen. You imagine the scientists stepping outside after the celebration, the cold air hitting their faces, their eyes adjusting to the night. Above them, a different set of stars burns quietly, each one hiding a secret of its own. The universe, it seems, just opened one more door, and though tomorrow they'll argue over models and mechanisms again, tonight they simply stand together in the dark, smiling like children under a campfire sky. The impossible planet is real, and that realization hums in their chest like a second heartbeat, rethinking the cosmos, because after proof comes the reckoning. Once the cheers fade and the champagne goes flat, the real work begins. You drift through the aftermath like a quiet observer, watching as every neatly drawn model of planetary evolution starts to buckle under the weight of one glowing, defiant world. It's not just Ember 9 anymore, it's everything. If this planet can survive its star's death throes, what else have we underestimated? The papers come fast and furious. Journals fill with words like paradigm shift and revised formation sequence. Scientists who once specialized in comfortable things, stellar lifespans, orbital decay equations, now stare at their screens as if they've been handed a new language. The equations still balance, but the meanings have changed. Historians still argue whether the first major rethink came from the astrophysicists or the geochemists. The geochemists certainly feel vindicated. They'd long suspected that planetary cores are tougher than theory allowed. Iron remembers, one of them says at a symposium, holding up a slide of molten core simulations. You can strip the gas away, you can cook the mantle off, but the heart holds. It's half metaphor, half math, and everyone applauds anyway. Meanwhile, astrophysicists begin revisiting the life cycles of stars. If planets can survive red giants, maybe systems we thought were dead still harbour remnants. Someone digs up infrared data from ancient star clusters and finds faint hints, tiny rhythmic dips that look suspiciously like Ember 9's signature. Could the galaxy be littered with such survivors, hiding in the glare of elderly suns? The question electrifies the field. A mainstream historical echo comes to mind. When Copernicus proposed that Earth wasn't the centre of the universe, people didn't just rewrite astronomy, they rewrote themselves. Ember 9 feels like a smaller but no less personal Copernican moment. Humanity has learned once again that the cosmos is more stubborn, more creative, and far less interested in our definitions than we ever guessed. Then comes the quirky ripple effect. University students start naming their coding projects after Ember, their resilience workshops after the iron core. A band releases an album called Orbiting What Burns You. Even motivational posters appear online, a glowing sphere captioned, "Keep orbiting anyway." Science rarely makes good merchandise, but this one does. Within the community, the shifts go deeper. The models of planetary habitability widen, no longer limited to temperate blue worlds with oceans and atmospheres. Maybe life doesn't need comfort, one astrobiologist says in a documentary. Maybe it just needs endurance. Suddenly the hunt for life expands to include the survivors. Rogue planets, scorched cores, moons circling pulsars. The definition of possible keeps stretching. Historians still argue whether this philosophical expansion was inevitable, or if Ember 9 simply arrived at the right moment, when humanity was ready to hear it. Climate change, extinction, and technological fatigue had already primed the world for a story about survival. The discovery just gave it a cosmic stage. Back in the research hubs, a new generation of telescopes is being designed. They'll tune their sensors to the wavelengths that Ember 9 taught us to watch. The telltale glow of stripped cores, the faint magnetism of survivors. One engineer calls the new project a graveyard survey, then quickly amends it. No, not graveyard. Afterlife. The name sticks. Theorists too begin softening their language, where once they wrote impossible, now they write currently unexplained. The humility feels good. It's as if the planet has reminded everyone that science isn't about control, it's about wonder you can measure. A mainstream historical fact slots neatly here. In 2015, gravitational waves were finally detected a century after Einstein predicted them. The proof didn't just confirm theory, it changed what counted as observable. Ember 9 has done the same for planets. What was once invisible, worlds orbiting dying stars, is now measurable, audible, tangible. And of course the debates continue. Is Ember 9 unique or common? Was its survival pure luck or a law we've only just glimpsed? Some argue that its moon, ash, if it exists, must have stabilised it. Others think magnetic coupling did the trick. The truth may be a cocktail of every idea ever argued in every late-night lab meeting. The point is no longer which model wins, but how many new ones will bloom. You imagine drifting through those meetings again. Equations sprawl across whiteboards, diagrams of stellar envelopes curl like vines. The scientists' conversations sound less like debates now and more like storytelling, chapters of the same saga told from different sides of the fire. The public too has evolved in its gaze. News articles no longer shout about impossible planets. They whisper instead about unexpected survivors. The tone has changed from disbelief to respect. One headline sums it up perfectly. The universe is older, hotter, and more forgiving than we thought. Historians still argue whether that forgiveness is metaphor or physics, but you can't deny the shift. Even cynics find themselves looking up at the night sky and wondering which of those stars hides another Ember 9, quietly orbiting, quietly teaching patience. And there's another effect, more personal. Many of the researchers involved admit privately that they've started seeing the world differently. One says she no longer fears failure as much. If a planet can lose everything and keep orbiting, she writes in a late-night email, maybe I can survive peer review. The ripple keeps spreading. Philosophy departments publish essays about resilience as a cosmic principle. Psychologists talk about orbital persistence as a metaphor for endurance under stress. Even theologians weigh in, calling Ember 9 the planet of grace. The scientists roll their eyes, but they can't help smiling. The interpretation, like the planet, endures. Finally, you picture that world again, small and glowing in its eternal ellipse. Around it, the red giant still flares, but somehow the light looks softer now. The planet hasn't changed. We have. Where once we saw contradiction, we now see balance. Where we saw failure, we see adaptation. Perhaps that's the final gift of Ember 9. Not to prove anything, but to remind us that every time we find something that shouldn't exist, we've really found a new version of ourselves. The planet that taught humility, because by the time the models settle and the conferences end, what remains isn't triumph, but perspective. You drift once more through the dark toward the quiet gleam of Ember 9. The star still swells in size, the planet still circles in its molten patience, and all across the small blue world that discovered it, minds are quieter now. The noise of argument has faded to a hum of reverence. Historians still argue whether that reverence belongs to the planet itself or to the reminder it offered, that the universe does not answer to us, and that this is its mercy. In every language of science, humility means the same thing, knowing how small we are in equations that keep running whether we're looking or not. For a while, the discovery lives everywhere. Museum domes project Ember 9's orbit in slow motion. Kids sit cross-legged under the red light and whisper questions about how it feels to be so close to fire. Teachers smile and say, "It feels like surviving." The planet becomes a story we tell children about persistence, not as metaphor but as math. Orbital decay postponed, gravity balanced by grace. A mainstream historical echo sits at the heart of the retelling. When the Apollo 8 crew first orbited the Moon and saw Earth rise, a blue marble above grey desolation, humanity finally understood fragility as beauty. Ember 9 offers the same mirror in reverse, beauty as endurance, even in desolation. And then the quirky modern footnote: someone builds a digital clock synced to the planet's orbit. Every 2.97 Earth days, when Ember 9 completes another lap, the clock's face glows red for 1 minute. Another orbit survived, it reads. People start using it as a reminder to pause, to breathe. Offices install them, therapists recommend them. The rhythm of a world 100 light years away becomes a heartbeat on desks and wrists. In academic journals, the tone softens. Where once sentences began with certainty, now they begin with curiosity. Perhaps. It is possible. Further study may reveal. The planet has taught scientists to speak with gentler verbs. It's a rare linguistic evolution, born not of weakness but respect. The final report from the Discovery team begins without flourish. We confirm the persistence of an ultra-short period remnant planet orbiting a post-main sequence star. But buried in the conclusion is a single human line. It is humbling to be noticed by a universe that owes us no explanation. You picture the lead scientist reading that aloud at the closing ceremony of an astrophysics symposium. No grand gestures, just a quiet pause at the end. The audience, usually so eager to question, simply sits in silence. Someone records the moment. Later, millions watch it online and feel that same strange peace, like listening to a lullaby made of math. Historians still argue whether humility can be measured, but they agree this discovery increased the sum total of it on Earth. In the years that follow, the research continues, but the urgency fades. Ember 9 becomes part of the background sky, catalogued but not forgotten. Students use it as a calibration target. Journalists reference it as shorthand for wonder that refuses to obey, and somewhere in the cold of a data center, its light curve keeps repeating: dip, rise, dip again. You hover one last time above the planet. Its surface ripples like liquid glass. The red giant looms so close that light and gravity blur into one endless sunrise. The air, or what remains of it, shimmers with ionized dust. Every orbit sheds atoms that will one day drift free and join the galaxy's clouds. Raw material for new stars, new worlds. Even destruction recycles itself here. And you realize the humbling truth. Nothing is wasted. Even impossibility feeds the next beginning. The molten iron you see now might, billions of years from this moment, cool into the crust of another planet circling another star, perhaps even under another watcher's telescope. A mainstream historical fact brings the circle home. The calcium in human bones, the iron in your blood, the gold in every ring, all forged in stars that lived, swelled, and died. The elements of Ember 9 are the same. We are quite literally made of survivors. The quirky detail that closes the legend is almost tender. In 2037, an amateur radio group begins broadcasting faint pulses toward the star every 2.97 days, timed to the planet's orbit. A symbolic echo, a human handshake across light years. They never expect a reply. They just want the universe to know it's been heard. Now, as you drift farther back into the velvet dark, the planet shrinks to a dot beside its red giant, then to a shimmer, then to memory. Around you, countless other suns burn quietly, each hiding something we haven't yet imagined. You feel small, yes, but also infinite, part of the same stubborn physics that lets a world keep orbiting against all odds. So you close your eyes. The hum of your fan or the whisper of night outside your window blurs into the sound of that distant orbit. The light fades gently, not as ending, but as promise. The last image you hold is of a single ember circling endlessly, patient as time, proving that even the universe can surprise itself. And now the light softens, the fire dimming to a glow you can hold in your mind without burning. You feel yourself drifting backward through everything you've seen tonight. The molten world, the swelling star, the shimmer of magnetic tides, each image folding quietly into the next until all that remains is warmth. The room around you steadies. The hum you hear might be the echo of that orbit, or maybe it's just your own pulse finding the same rhythm. Either way, it's steady, dependable, older than thought. You let the story's noise fall away. The scientist with their coffee, the data humming through fibre optic veins, even the fierce arguments about what's possible, all of it softens into a single idea, that persistence, whether in iron or in breath, is its own kind of peace. In that peace, you imagine Ember 9 completing another lap around its star, 3 days to circle eternity. The motion is slow, certain, unhurried. You follow it once, twice, until the glow becomes a faint red thread drawn across your inner sky. If you listen carefully, you might notice how the quiet feels heavier now, as if the universe itself has settled under a blanket. The same gravity that keeps planets in orbit keeps your thoughts from drifting too far. The same physics that balances fire and motion balances the small world of your heartbeat. So breathe once more. In, out. Let the stars dim behind your eyelids. The impossible still exists out there and within you, but it's no longer loud. It's just steady light, patient and sure, waiting for tomorrow to rise. Good night, traveller, sweet dreams from the edge of an impossible orbit.